So, hello everyone, and welcome again for the live session for the NPTEL course Introduction to Semiconductor Devices. So, this is the 12th live session, and indeed the last live session from my side for this particular course. So, this course, as you know, is instructed by Professor N.K. Emani of IIT Hyderabad, and I am Samadhan, your PMRF TA, for conducting these live sessions. So, as the session goes, in the first 10 minutes or so, I'll briefly cover the lecture content, basically this week's recap, so that gives you a quite quick refresher in moving forward when we're solving the assignment problems. And then we'll move to the problem solving, which is parallel from the previous course offering, and which is quite similar to your current set of assignments, and of course your end semester examination. I hope you must have gotten that mail of end semester examination registration and so on. Okay, so let me just admit someone. Okay, so without further ado, let's get started with the short recap of this week, that is week number 12. So as I've already said in the last session, that in the first 10 weeks of the course, like the majority of the course, we have looked at the electronic devices, few large number of them, in which we have understood how to analyze them, their properties in quite sufficient depth, I believe. And we have promised that in the last 2 weeks of the course, we'll focus on the optoelectronic devices because of their importance in the current technology. So in which we see solar cells, LEDs, lasers, photodetectors, all of these are the photoelectronic devices. And especially we can apply the concept that we have learned so far in the like first 10 weeks of the course to understand how these devices, the optoelectronic devices, work. So there are two classes of optoelectronic devices. First, in which the device which converts electrical energy into light energy, and the other in which the light energy is converted back to the electrical energy. So in the last week, that is week number 11, we studied the photodetectors, in which the light energy is converted into electrical energy, and in this week, that is the week number 12, we'll see how the class of optoelectronic devices in which the electrical energy is basically converted into the light energy. So basically in this week we'll understand light emitting devices. So far we have understood fundamentals of it, and we'll now focus on the light emitting devices. So what are the fundamental mechanisms of light absorption and emission is the question that we encounter first. Give me a moment. Yes, so I hope you can see my slide. So we have covered the light absorption in some in detail in the last week itself, where we saw that when a semiconductor is illuminated with light, the photons may be absorbed or they may propagate through the semiconductor depending on the photon energy and the band gap energy, that is Eg. So if the photon energy is less than the band gap energy, the photons are not readily absorbed, and in that case the light is transmitted through the material, and the semiconductor or any material seems or appears to be transparent. And if the energy is more than the band gap energy, photon can be absorbed as it interacts with the valence electrons and elevate the electron into the conduction band. And the probability of this particular interaction, that is absorption, is higher when the incident energy is larger, way larger than the band gap energy. So this interaction creates an electron in the conduction band and a hole in the valence band, which is nothing but our electron hole pair. Okay, so this is about the absorption process, and the way we can understand the absorption process, and we try to model it by writing a rate equation for it. So what is the rate of decrease of electrons in the lower state is the question that we encounter, and we can write it as let us say the derivative of n1 with respect to time. So n1 is the number of electrons in the ground state. So dn1 by dt gives us the rate of decrease of electrons in the lower state. So this will definitely be proportional to the n1, that is number of electrons present in the ground state, and also it will be proportional to the intensity of the light that you are shining. So that will be represented by a term which we represent by rho v, which is essentially capturing the spectral density, let us say the energy density here. And definitely the number of electrons in the ground state will reduce, and so we'll put a minus sign. And finally there is one last term, which is the coefficient, and nothing but the Einstein coefficient B12, transition from 1 to 2, that's why it is B12. Similarly, if you go to the spontaneous emission process, let us say if you take the example of a semiconductor, you can think of a scenario where there are number of electrons in the higher state already and there are corresponding holes in the lower state. So what will happen in this particular scenario? Well, the electron in the higher state can give up that particular energy and come down to a lower state. Just a moment. Yeah, so the electron will come down to a lower state, and how much is the energy of the photon that is emitted? Well, it turns out that it is equal to the energy difference between these particular levels, that is E2 minus E1, or say delta E. So the difference in the energies between the highest state and the lowest state, let us say the energy of the highest state is E2 and the lower state is E1, the photon that is emitted is actually turning out to be E2 minus E1, that is the energy of the emitted photon. So this process is also is the spontaneous emission, and this is one of the emission processes wherein without doing anything, just the material, if it has electrons in the higher state, there will simply de-excite and give you a photon. So for this process also we can write the rate equation, and rate equation as seen here. So you can see that the rate of decrease of electrons in the higher state n2 for the number of electrons in the state E2. So that is given by this particular relation where A21 is again Einstein coefficient for spontaneous emission, and we can write this particular rate equation with respect to the ground state as well, so in which the number of electrons would be increasing, so it is a positive sign here. So these two equations are equivalent to each other. Going to the the last emission process, which is nothing but the stimulated emission. So the last process, the simulation emission. So what happens there is, instead of just having the material to de-excite, you shine a photon onto it. And so for example, as can be seen here, that we are shining a photon of energy, say h cross omega, having energy h cross omega. So this energy is incident on a material. So what will happen is, suppose it has the same scenario of many electrons in the highest state and there are corresponding holes in the lowest state. So you have the scenario available. So then when this photon is incident, it will cause the emission of a second photon, which is a coherent photon. So what I mean by that is, the second photon that is emitted has the same phase and the frequency as the incident photon. So same phase and frequency. So this is a coherent photon that is emitted. So, and that is why we call it a stimulated emission process, because essentially the photon that we are incidenting is stimulating the emission of another photon. So this particular mechanism can also be written in terms of a rate equation that can be seen in this particular equation. Okay, so these are the three fundamental mechanisms of interaction of the radiation with matter. So these Einstein coefficients are not really independent. A21, B21, etc. are not really independent. they are related to each other, and if you know one of them, you can find out the other two, and the relation is given in this particular box here, essentially telling you that A coefficient is related to the B coefficient. So the stimulated emission is going to control the spontaneous emission, and so on. So if you know, let us say B12, we can determine both B21 and A21, or any one coefficient is what you need to determine the other two coefficients. So going to this particular box here, after these radiative absorption and emission processes, we moved to the important process of electro and photoluminescence, in which when excess electrons and holes are created by photon absorption, photon emission from the recombination process is called the photoluminescence, and electroluminescence on the other hand is the process of generating photon emission when the excitation of excess carriers is a result of an electric current caused by an applied electric field, of course. Especially we are mainly concerned here with the injection electroluminescence, in which the result of injecting carriers across a PN junction. So the light emitting diode and the PN junction laser, the PN junction laser diode are examples of this particular phenomenon. So in these devices, electric energy in the form of a current is converted directly into the photon energy or the light energy. After that, we saw the band gap tuning by mole fraction. So we have the direct band gap semiconductors, and their mole fraction can be adjusted to give a particular band gap, and we know that the band gap is essentially related to the uh, uh, wavelength of a photon that is emitted by that particular compound or a semiconductor. After that, we moved to this special class of devices, the light emitting diodes, and we saw their internal and external quantum efficiencies. These are quite important. We'll see a problem based on this in the problem session. After that, we moved finally to the lasers, which is acronym for light amplification by stimulated emission of radiation, in which we saw what are different prerequisites or the necessary conditions for lasing actions, in which the stimulated emission is one, the inversion of population, in which the number of electrons in the higher state is more than the lower state, and also the optical gain and pumping mechanisms that are necessary for the lasing action that we saw. Okay, so with this, I think the summary of week 12 is concluded, and we'll directly move to the problems now. Okay, so the first problem, I think these the problems for this particular week are fairly qualitative, so not much of a calculation. So first problem is, which of the following statement or statements is or are true with respect to lasers? So you can unmute yourself and try to give the answer for this.
B.
Okay, so first is the B, that is the coherence that we saw, that the emitted photon is also in a coherent state with uh, the photon that is incident. Okay, one more, that is one. What else you think? What about the
C. Next one.
sorry?
Option C.
Okay, exactly. So as we saw that there are a couple of mechanisms of emission, stimulated and spontaneous, but for the lasing action we want stimulated emission to be dominated, and that is one thing. Okay, so Kyle is saying monochromatic source, exactly. So we saw that the emitted photon has same wavelength as the incident photon, and the bandwidth we can say is quite small, like the emitted wavelength is indeed at max of about 1 to 2 nanometers. So for practical purposes we can say that it is a monochromatic source of light. What about these two? So this is
Last
about application. I think it is optical communication in the optical fibers and etc. The lasers play quite an important role. Okay, so I think this is about question number 1. Let us go to question 2 then. Okay, in the context of radiative processes, semiconductors can be modeled as. So we have seen it already. So if you take any material, let's say a semiconductor, you have the conduction band and the valence band. So we could think of it as a two-level system, so that okay, so the above level is represented by the higher energy, and the level below, which is the valence level, represented by uh, lower energy, having n1 n1 and n2, the number of electrons in these particular energy levels. So we can model the different processes that we have seen in the form of a two-level system. For the case of semiconductors, and the ground state is the valence band, and the excited state is the conduction band. So the two-level system model is a way of representing the simplest model of representing the optical system or optical material. So we saw that on a two-level system, if you have a photon incident, what happens is it turns out that there are three different processes that can happen, and we have studied it in detail. So to summarize, in the context of radiative process, the semiconductor can be simply modeled as a two-level system. This is fairly straightforward. Let us move to then question number 3. Okay, so this is a 2-mark question. There are two statements given, statement number 1 and 2. So we have to analyze these two statements and tick the correct answer. Okay, first statement is, it is difficult to build a blue laser compared to red laser. And the statement 2 is, spontaneous emission becomes stronger with increasing frequency. Okay, so for this, I think let us analyze it in some detail. So if you look at the expressions for A21 and B21, if you go to the summary slide, okay, so for the expressions for A21 and B21, there is a term of frequency. So frequency dependence is seen here. So everything else is the fundamental constant, but the spontaneous emission seems to increase as a function of frequency. So it is directly proportional to the frequency cube. So this is very important because we might have seen that red lasers, green lasers, but it is quite difficult to build blue lasers. And because if you know that frequency of red lasers is low and the frequency of blue is higher, so it is, yeah, so the frequency of blue is quite higher, and as we saw that A21 is directly proportional to the frequency. So it turns out that as you go to the higher and higher frequencies, in our case the blue region, the spontaneous emission process becomes very strong. So there are two processes which are competing with each other. So for higher frequencies, uh, spontaneous emission is dominating. It dominates at higher frequencies. Okay, so this A21 spontaneous emission is strong at higher frequencies, and because of which it is difficult to build lasers as we want stimulated emission to be dominant one. So we want emission to be coherent, and just a moment. Yeah, so we want stimulated emission, and we want the coherence, and we want photon that is emitted to have the same frequency and phase. So the stimulated emission is essential for the laser, and that becomes hard, or that becomes less compared to the spontaneous emission for higher frequencies. So that is the reason the spontaneous emission is much stronger in the blue frequencies, and it is difficult for us to build a blue laser compared to the less red laser. So both statements S1 and S2 are true, and indeed S2, which says that the spontaneous emission becomes stronger with increasing frequency, is the correct explanation of S1. Okay, So this is the answer for question number 3. Okay, so let us move then to question number 4. This is a 1 mark question. It goes as follows. The radiative and non-radiative lifetimes of an emitter material are given by tau r and tau nr respectively, and it is asked that in which of the following cases will the material be an efficient light emitter. Okay, so for this let us analyze our spontaneous emission equation first. So we saw that for spontaneous emission dN2 by dt is A21 times N2, and if you solve this, we take integral on both sides, we'll get the solution as N2t with respect to time you are integrating is N2 at time t is equal to 0 and exponential of minus A21 times t, which is time. So if you look at it, we'll immediately recognize that this is something similar to the rate equations or the decay equations that we have seen many times. So rather the exponential decay that we have seen, we could write it as, this could be simply written as N2 naught exponential of minus t over tau, where tau is 1 over A21. Okay, so this is going to be equal to 1 over A21, that is tau, and it is nothing but the radiative lifetime. In our case it is spontaneously emitted, so it is tau r. It is radiative lifetime. Okay, so essentially how much time it takes on average for an electron to be excited, excited electron to emit a photon is given by this particular parameter. So this is how the radiative decay happens. There is also going to be something called as the non-radiative decay, and it is as follows. So your electron, instead of emitting a photon, it could simply just lose its energy to lattice, and so in a sense your electron can lose its energy to the lattice vibration and just come to the lower state and get captured. So that is called as the non-radiative decay process. So in the non-radiative decay, electron loses its energy to the lattice, and this is also going to be present, of course, and we would like to have radiative decay to be more because we want the photons to come out, not the phonons. And if when we you say non-radiative is losing the lattice, that means we say phonons to phonons, it is essentially heat. So it is heating the semiconductor material, which we are not interested in. So we can write this particular rate equation in terms of both radiative and non-radiative lifetimes as dN2 by dt is simply the combination of tau r and tau nr. Now to analyze our problem, okay, so if your tau radiation is much smaller, let us say your tau r is smaller than tau nr. If tau r is smaller than your tau nr, that means radiation takes place. What it means is that is going to when our tau r is small, then there is going to be this particular parameter is going to be larger, and basically this is going to be large means the light emission is efficient. So in this case what happens is light emission is efficient in a way that we are saying that A21 is large indirectly. So you want it quickly emit light, you want quickly emit photons. So these two processes again are competing with each other. If non-radiating lifetime is larger, so before it radiates non-radially, the radiative lifetime, as it is smaller, it favors the emission of photon instead of a phonon. So if you consider other scenario where tau r is much greater than tau nr, what happens is that it means that it is taking more time for electrons to emit a photon, but instead before that it will actually non-radiative decay into phonons. So that is not what we want. For the material to become essentially a efficient time emitter, we want the radiative lifetime to be quite lesser than the non-radiative lifetime. Okay, so this is about question number 4, and then we will move to question number 5. This is something for a small calculation. So the objective of the question is as follows. We want to determine the output wavelength of a gallium arsenic phosphor material for two different mole fractions, and in which we first consider the gallium arsenide first and then the other material. Again, we have seen we have given a energy gap as a function of Eg as a function of mole fraction here for our reference. So we know that for the gallium arsenic, the band gap Eg for gallium arsenic is 1.42 electron volt. So we want to first determine the wavelength that it would emit. So this material would produce a photon output at a wavelength of, we know that lambda is inversely proportional to the energy, that is band gap. So in terms of electron volt, it is simply 1.24 divided by the energy, that is Eg. So 1.24 over 1.42, which is nothing but 0.873 micrometer. So this is the wavelength of emitted photon of a gallium arsenic material. Now let us consider the other material. The wavelength, you can see that this particular wavelength is in the infrared range and not in the visible range. So if we desire a visible output with a wavelength, let's say lambda of around 0.653, which is for a red color, for example, the band gap energy would have to be, again if we just substitute in the same equation, lambda will get the band gap energy has to be 1.90 electron volt, and this is achieved. This band gap energy would correspond to a mole fraction of approximately x is equal to 0.4. So the gallium arsenic cannot be a material for the photon in the visible range. For that, the energy band gap is quite lower. We want energy band gap of 1.9 electron volt to get a photon in the visible range, and this corresponds to, as you can refer to this particular figure, that 1.9 corresponds to, so somewhere here 1.9 corresponds to mole fraction of about 0.4. Above that it becomes indirect band, so it doesn't give us the lasing action. So this is the maximum and it corresponds to about mole fraction of 0.4. Okay, so let us move to question number 6, which is a common data question for question number 6 and 7. So consider the IV characteristics of various excuse me, diodes made up of different materials as shown in the figure 1 below. Okay, so different diode current versus diode voltage for different materials is shown, and we have to analyze this particular figure for next two questions. So the question number 6, based on the particular IV characteristics, is as follows. Which of the following diodes can be used as LEDs is the question, and the hint given is that we have to see that which are the direct band gap semiconductors. So we've seen that the direct band gap semiconductors are the ones used in the LEDs. So if you just see the figure, we have know that the gallium arsenide, gallium arsenide phosphate, and gallium indium nitride is the direct band gaps. Hence, that will give us the LEDs that can be used as the LEDs. So the point of the device is to create photons from an electron hole pair, and it would be highly inefficient to introduce extra energy for the electron and hole to recombine, and for these reasons indirect semiconductors are not likely to be used for LEDs. So if you analyze why direct band gap semiconductors are essential for LEDs, so whether you get an energy in the form of a photon, that is light, or not depends on the semiconductor material. So there are semiconductors with a direct band gap or an indirect band gap. So as we know that band gap is the energy difference between the conduction band and the valence band, in which a direct band gap means that the minimum of the conduction is directly above the maximum of the valence band, that is the delta k is 0 for the direct band gap semiconductor, and for the indirect band gap the minimum of the conduction band is not exactly above the top of the valence band, and for that case the delta k is non-zero. And for example, the gallium arsenic, if you consider, has a direct band gap, and silicon on the other hand is an indirect band gap. So the minimum of the conduction band and the top of the valence band have the same k vector at the direct band gap semiconductor devices, and the k vector is related with the momentum, that is p vector. By the formula we know that p is nothing but h cross k. So the momentum of the holes and electrons is the same at a direct band gap, and no momentum has to be transferred at the recombination. So you get an energy in the form of photon at the recombination. But if you have an indirect band gap, the electrons and holes have a different k vector, and so a momentum has to be transferred. So you will get a lattice vibration, which means you will get the energy in the form of a phonon at the recombination. If you can summarize, we'll see that the direct band gap semiconductor we get photons, and for indirect we get phonons. So we know that gallium arsenic phosphorus, and indium are the direct band gap semiconductors, giving us the LED action. So these can be used as LEDs. So based on the same data, we have question number 7, and it is as follows: choose the correct statement with respect to the wavelength of light emitted by diodes. Okay, so their band gaps are shown. If you see this particular figure, their band gaps, just a moment, yeah, their band gaps are also indicated here, and we can see that the band gap of this one is higher than for gallium arsenide phosphorus, is higher than for gallium arsenic. We won't consider germanium and silicon, as we saw that these are indirect and these will not be used in the LEDs. So also we saw that in the previous problem that energy and wavelength are inversely proportional to each other. So using this particular relation, we can directly infer that the lambda for the gallium arsenic would be lower as compared to lambda for the gallium arsenic phosphorus as compared to lambda for gallium indium and nitride, because the energies are exactly opposite, that are inversely proportional to the lambda. Okay, so this is about question number 7, which was based on the IV characteristic. Let us then go to question number 8. So let us just introduce these concepts first, and that will straightforwardly solve this particular problem for us. So the internal quantum efficiency of an LED is the fraction of diode current that produces luminescence. So the internal quantum efficiency is a function of the injection efficiency and a function of the percentage of radiative recombination events compared with the total number of recombination events. So one very important parameter, other parameter is the external quantum efficiency, which is the fraction of generated photons that are actually emitted from the semiconductor. So the emission is the important thing to be noted here. The external quantum efficiency is normally a much smaller number than the internal quantum efficiency. Once a photon has been produced or generated in the semiconductor, there are different losses, three losses in particular, three loss mechanisms in particular, in which the photon may encounter. First is the photon absorption within the semiconductor, second is the Phrenal loss, and third is the critical angle loss. A photon can be emitted in any direction. For the spontaneous emission, we are seeing the LEDs, so that can be emitted in any direction, and since the emitted photon energy must be higher than the band gap energy, these emitted photons can be reabsorbed within the semiconductor material. So that is quite a disadvantageous and lossy term for us. The majority of photons will actually be emitted away from the surface and gets reabsorbed in the semiconductor material itself. So this is about one loss mechanism. Considering the second case, that is the Fresnel loss, the photons must be emitted from the semiconductor into air. Thus, the photons must be transmitted across a dielectric interface, and there are different parameters. Let's say N2, which is the index of refractive, that is index of refraction, that is refractive index for the semiconductor, and N1 is the index of refraction for air. So N2 refractive index for the semiconductor material. So we are seeing the Fresnel loss, and N1 is for air. Okay, so the reflection coefficient we have seen is given by N2 minus N1 by N2 plus N1. So reflection coefficient means the fraction of incident photons that are reflected is given by this particular term, and this effect is called as the Fresnel loss, and the reflection coefficient lambda is the fraction of incident photons that are reflected back into the semiconductor. So we want this reflection to be minimal, so that we get our photons emitted in the air. So this is another loss mechanism, and the third loss mechanism, as we saw, is the angle loss. So the photon incident on the semiconductor air interface at an angle are uh, gets refracted, and if the photons are incident on the interface at a particular angle which is greater than the critical angle, the photons experience total internal reflection, and the critical angle is determined from the Snell's law, and it is given by theta c is sine inverse of n1 by n2. This is what we are seeing, the critical angle loss. Critical angle loss. So these are the different loss mechanisms. So particular to our problem, internal quantum efficiency, to summarize, we can say that is the number of photons generated divided by the number of carriers injected, and the external quantum efficiency can be defined as the number of photons extracted from the number of photons generated. So there are number of photons generated, but we want them to be extracted, and that is given by the external quantum efficiency. So I think we want to see these losses. Let's take a problem based on these two losses, so that this particular concept will become concrete. Okay, So based on these quantum efficiencies, we have question number 9, which is our last question. So the question number 9, let's say 9A, is as follows. Calculate the reflection coefficient at a semiconductor air interface. So we'll consider the interface between a gallium arsenide semiconductor and air. So the refractive indices which are given are as follows. The index of refraction for gallium arsenic is, which is N2, is 3.8, and we know that for the refractive index of air, that is N1, is simply 1. Also the wavelength is 0.7 for corresponding to lambda of 0.7 micron. Okay, so we saw that the the reflection coefficient is given by N2 minus N1 over N2 plus N1 whole squared. If we just substitute the refractive index here, 3.8 minus 1.0 divided by 3.8 plus 1.0 whole squared will get lambda of 0.34. So it means that about 34% of the incident photons will get reflected. So 34% is the loss that we would face, and that is encountered in the, that is like seen in the external quantum efficiency, one of the parameter. So we can say that the reflection coefficient of 0.34 means that the 34% of the photons incident from the gallium arsenide onto the semiconductor air interface are reflected back into the semiconductor. So this is something that is a lossy parameter. Now going to the second problem, that is B. The objective is as follows. Calculate the critical angle at a semiconductor air interface. Again, considering the gallium arsenide, and N2, we saw that N2 is 3.8 for lambda of 0.7 micron, and N1 is again 1. Okay, so let us calculate the critical angle that we have mentioned in the previous slide. It is nothing but sine inverse of N1 over N2. If we just substitute the refractive indices, that is sine inverse of 1 over 3.8, which is nothing but 15.3D. Okay, so any photon, what it means is that any photon that is incident at an angle greater than 15.3 degree will be reflected back into the semiconductor. So these many photons which incident at angle higher than the critical angle will be reflected. So this corresponds to the critical angle loss, that is again incorporated in the external quantum efficiency. Okay, so this is about the problems that I was supposed to solve, but I think since we have 5 more minutes, I think I'll solve one more problem. Let us call it a bonus question. So it is as follows. Consider a 3-level laser emitter which emits a wavelength of 5500 angstrom. So there are 3 sub questions. First is, what will be the equilibrium ratio of the population of the upper level to that of the lower level at T is equal to 300 Kelvin? Okay, so the given lambda, if we solve, given lambda is 5500 angstrom and the temperature is 300 Kelvin. We know that from the Boltzmann distribution, N2 over N1 is nothing but, it is an exponential parameter, minus hc over lambda kt, where k is the Boltzmann constant. Well, it can be written as hc by lambda is nothing but delta E or h nu. If you just substitute all these parameters now, exponential of minus h is the Planck's constant 6.63 times 10 to the power minus 34 times c is the speed of light 3 times 10 to the power 8 divided by the lambda, that is 5500 times 10 to the power minus 10 meters. We are writing it in the SI units times the Boltzmann constant given by 1.38 times 10 to the power minus 23 times the temperature, that is 300 Kelvin. So if you just solve it, we'll get the N2 by N1 as 1.32 times 10 to the power minus 38. This is at T is equal to 300 Kelvin. So you can see that this is extremely small number. So at around room temperature, there is extremely low probability that the electron in will see the electron in the higher level N2 as compared to the N1. So this is especially the fraction you can see, and it is quite small. So let us solve sub question B. At what temperature the above ratio would be half? This ratio we want to be half, and we want the temperature that will correspond to it. So again, using the same equation, on the LHS we have half because we want N2 by N1 to be 0.5, and again if you just substitute it, exponential of minus 6.63 times 10 to the power minus 34, and all these parameters I am not going to substitute, and this is temperature. Okay, ln of 2, it will be simply hc over lambda kt. We are just simplifying the same equation. So temperature, if we solve for temperature, it will be simply hc over lambda k ln of 2. So if you just substitute all these constants, you will get the temperature required for this ratio to become half as 37749 Kelvin. So you can see that this is a ridiculously high temperature. So more than 37,000 degree Kelvin is the amount of temperature required for this ratio to be become only half. So like 50% of them to be on the higher side, we want this much of the temperature for this particular condition to take place. So we need to raise the temperature to a value of, let's say, 40,000 Kelvin just for having 50% population in the excited state. So that means population inversion cannot be achieved by thermal excitation. So we can say that the thermal excitation is extremely inefficient method for the population inversion, and hence we have to look for other methods like the optical pumping and other pumping mechanisms that we have uh, seen in the regular lectures. If you have any doubt, please feel free to ask. So it has been a wonderful experience for me to conduct this live session. It was the last live session for this particular course, but I'll be posting like informative things on my YouTube channel, so be subscribed to that. But for this particular course, I think that's it from my side. Okay, so this brings me to my final slide. Then thank you everyone again for joining for this particular live session. Indeed, it was the last live session from my side for Introduction to Semiconductor Devices course. Indeed, it has been quite experience for me to conduct these live sessions. Thank you so much again for joining live, and yes, that's it from my side for this particular course, and thank you so much and have a nice day.